Good morning, everyone. Today we will talk about ionizing radiations. We will introduce some parameters, including the decay constant, the half-life, activity, and we will also talk about the carbon dating and its role in detecting the date of the death. In radioactive decay, we have seen that nuclei are decaying exponentially. Some of them they take long time to decay. Others they take short time. So some of them are quickly decaying. Some of them are slowly decaying. All the decaying is happening exponentially. And we also have seen that some of the nuclei that are stable, which are the blue ones here, the green ones are long-lived. However, the yellow ones are short-lived, and the red ones are intermediate. But at the end, all of them are decaying exponentially. So if we look at this exponential decay between two different materials, one of them is decaying faster than the other one, we will notice that the blue one is decaying in a slower rate than the red one, decaying, reaching the zero level. So in order to characterize this decay, we have seen that this number of the nuclei, that is we call initial, will start to decay exponentially, such that the lambda here is called a decay constant, and it's given per unit time. We will see sometimes we use the minute, sometimes we use the second, it depends, sometimes the year. The number of the radioactive nuclei present is given by NT. So the number of the nuclei is a function of time, and we said that the N naught is the initial number of the nuclei. So here we can see that the decay constant lambda is 0.116 per minute, while the blue ones is 0.0578 per minute. So if this one is 1 and this one is 2, we can see that lambda 1 is greater than lambda 2. And here the decay time for the function lambda 1 is happening faster than for the function of lambda 2. So the number of the radioactive nuclei that we have seen is a function of time. We can also define another parameter that we call half-life. This half-life is the time it takes to transform half of the initial number of nuclei in my function. So half the time, if the number of the nuclei is 6 to the power 23, then the half time is the time we measure right when half of the nuclei number is transformed or decayed. So this is the half. This is 6 to the power 23. This is 3 to the power 23. So this is the half time. This one is T half. If I call this one 1, and this one is T half for number 2. So the half time and the decay constant, they are related to this expression here. I have the half time equals to the natural logarithm of 2 divided by lambda. Develop this expression by taking the half of this n t equals to n naught e to the power minus lambda t. Then if you substitute this nt with half n naught equals n naught e to the power minus lambda. And now this time would be t half. Then work out this equation, solving for t half, you will get that t half equals to natural logarithm of 2 divided by lambda. So here n is going to cancel. Take the natural logarithm for both sides. Then this one is natural logarithm of half equals to minus lambda t half. Then t half would be natural logarithm of half divided by minus lambda, or t half as minus natural logarithm of 2 divided by minus lambda, and here t half as natural logarithm 2 divided by lambda. So this is how we got this expression. So if you substitute now lambda with its equivalent, and in this equation we have lambda from here equals to natural logarithm of 2 divided by t half. Take this one, substitute it here, you'll end up with this expression. It is important to know how did we derive such expressions. You don't have to know how to derive it, but it's useful to know where did those numbers and variables come from. Okay, so let's move to this example. In this example, we have the nuclei S37 has half-life of 5.1 minutes. The question is, what is the decay constant of this nuclei? We need lambda. What percentage of the sample is remaining after 32 minutes? So here we have the half time as 5.1 minutes. We need lambda. We said here 2 half as natural logarithm divided by lambda, and lambda equals to natural logarithm divided by the half time. Lambda equals to divided by 5.1, and this lambda equals to 0.136 per minute. Then we know the nuclei number nt equals to the initial and node e to the power minus lambda t. So we have nt equals to a node e minus 0.136 times 32, and nt equals to 0.0129 a node, or nt as 1.29% remaining of nt. Okay, next example, radioactive decay. After how many half-lives is a radioactive sample reduced to 1 over 128 of the initial number of the parent nuclei? We know the equation for the nuclei number equals to n naught e minus lambda t. If we have nt equals to 1 over 128, then by equating both expression, I have 128 and naught equals to n naught e minus lambda t, and naught is going to cancel, and then I need to calculate t, taking the natural logarithm of both sides. 128 equal to minus lambda t, then t equals to 128 divided by minus lambda. So if we calculate this is going to give me t 4.85 divided by lambda, because natural logarithm of 1 over 128 is going to be minus, then the minus is going to cancel. This will be the time. Now let's calculate the half time, which is the natural logarithm of 2 divided by lambda as well. So in order to know the time in terms of the half life, then I'll take the ratio, divide t by t half equals to 4.85 divided by lambda divided by natural logarithm of 2 divided by lambda. Lambda is going to cancel, and then I will end up with t equals to 7 half-lives. So the answer to this question is D. This example, we have a particular isotope that has a half-life of 4 hours. What fraction of the initial parent nuclei has transformed to daughter nuclei after 12 hours? So we want to know the nuclei, the fraction of the initial nuclei that transform to the daughter nuclei after 12 hours, not the remaining, the one that got transformed. We have the half time being 4 hours. We have lambda being natural logarithm 2 divided by half time, which means lambda equals 2 natural logarithm of 2 divided by 4 hours. We'll get this one in minutes, and then lambda would be 2.888 10 to the power minus 3 per minute. So this is lambda. Now, the nuclei number as a function of time is the initial number e minus lambda t. Okay, so here after 12 hours, then we have nt equals to n naught minus 2.888 10 to the power minus 3. This is per minute, so the time, my time here will be also minute. Then 12 hours times 60. Then NT equals to N naught times 0.125. Now this is the 12.5 here is the remaining. This is the remaining of the initial. I need the transformed, then the transformed is 1 minus 0.125, then N trans is 0.875 N naught, or N trans is 7/8. So this equation is always going to give me the remaining number of nuclei with respect to this decay function, which is exponential. If you subtract this ratio that you get here from 1, you will get the ratio for the transformed number of nuclei. So the answer here is E, 7/8. Now we will define a new parameter that we call activity A. This activity A is also a function of time that defines the rate of the decay. The rate of the decay. By multiplying the number of the nuclei, that's a function of time, with the decay constant lambda, taking the lambda here per second, then you get the activity, which is the rate of the decay, that is in decays per second. So lambda here has to be per second to get the unit of the activity as decays per second. Now, 1 decay per second, we equate it to a unit called becquerel. This becquerel, BQ, equals to 1 decay per second. However, we have to take the lambda here as per second in order to get the activity in decays per second. So if this is the number of the nuclei as a function of time that is remaining after the decay, then multiplying this with lambda that has a unit of per second, gonna give me this function. Now this is my activity function. Then I can substitute lambda with n naught with a naught this time, which is n naught times the decay constant as per second. Then this I'm calling the initial activity. A naught is the initial activity. The function is exponential, no difference. However, this function defines the rate of the decay. Now let's look at this example. In this example, we have nuclei Cl38 is produced in the atmosphere by cosmic rays. If 7.5 10 to the power 6 nuclei are produced at the same time, so this is my initial nuclei here, 7.5, 10 to the power 6. What is the activity of the nuclei in becquerel remaining after 5.5 hours? So remember, the function defines the remaining. So we need to find the activity in decays per second, which is the becquerel here, after 5.5. Half time is given to me as 37 minutes. So here I have the half time as natural logarithm 2 divided by lambda. Then my lambda is natural logarithm of 2 divided by half time. Okay, so here I will calculate the lambda per minute, which is, I have natural logarithm 2 divided by 37, which means lambda is going to be 0.0187. I also need the lambda to be per second. So in this case, over 37 minutes times 60, and then lambda. So let me, if I call this one minute, this one second, then the 1 per second would be 3.12, 10 to the power minus 4 per second. So I have this, and I also have this. As we'll see, we will use. Okay, so we have the activity A as lambda n naught E minus lambda T. So in this case, I have A equals to, this one has to be per second, then 3.12, 10 to the power minus 4 times n naught as 7.5, 10 to the power 6 times E minus 0.0187 times 5.5. This is hours. I will take it as minutes. Then the activity is 4.8 becquerel. The rule of thumb here is this unit, if it's minute, then this one has to be per minute. If you use this one as per second, then this one has to be in second. So here, for my lambda here, I used it as per minute, and I use the time as minutes. So I have 5.5 hours. I converted the 5.5 hours to minutes. Then this is how I got the activity function to be 4.8 becquerel. Now, if I am to rewrite this one just to make it here, I have A equals to 3.12, 10 to the power minus 4 times 7.5 and 6 times E 0.1 10187 times 5.5. So this one is per minute, and this one is minute. Then the answer is 4.8 becquerel. The carbon dating is basically utilizing this decay phenomenon for the carbon. The ratio between the C14 to C12 is constant over time, and it's given almost by 1 to the power minus 12. Organisms have the same steady state ratio while living. So as long as you have living creatures, then the ratio between the C14, that is called an unstable carbon, to the C12, that is a stable, is constant as long as this creature is still living. Once they die, then the C12 is going to stay the same, and the C14 is going to continue decaying. From the changing ratio between the C14 and the C12, you can find out the date of the death for this creature. So the decaying is happening exponentially, and the time equals to 0 is the time of the death. So once you have a death, then the C14 start to decay, and this ratio start to decrease. Now, C14 decays half time is 5.710 to the power 3 years, 5,700 years. Measuring the ratio between the C14 and the C12, substituting it in this equation here, you should be able to find the time for when the death happened. So if we call this carbon dating as RT, that is also a function of time. And then this constant ratio as R naught, then this function defines the decaying function for the ratio of the C14 to the with respect to C12. In this example, we have the ratio of the C14 to C12 in an ancient wooden bowl is 62%. So this is the remaining of the ratio of the present day organic material. So RT here is 0.62 R naught. How old is the bowl? If you know that the half-time of the C4 is 5.7 10 to the power 3 years. So here I have T half as 5.7 10 to the power 3 years. Now substituting in the equation, RT equals to R naught e to the power minus lambda T. Then also RT equals to 0.62 R naught. Then equating those, we will get 0.62 R naught equals to R naught E minus lambda T. R naught is going to cancel. If you take the natural logarithm for both sides, you get natural logarithm of 0.62 equals to minus lambda T. We know that Lambda is natural logarithm of 2 over half the time. Then substituting the time, the half time with 5.7. Then we have the lambda here as a unit of per year. So the lambda here becomes 1.216 or minus 4 per year. Now let's take this equation to here. So we have 0.62 equals to minus 1.216 10 to the power minus 4 times t. Then this one is per year. Then t equals to logarithm of 0.62 minus divided by 1.216 10 to the power minus 4. And t becomes 3,931.6 years. As long as you took this unit to be per year, then expect this time to be years. Also, take in your consideration that there are limitations of carbon dating. Carbon dating does not work accurately on samples that are more than 30,000 years. Why? Because there will be very little C14 left. The half time is way smaller than the 30,000 times. So by the you reach 30,000, there will be very little of C14 that will make the measurement inaccurate. Also, C4, the ratio itself went through changes during the past time due to some major events that happened in our history. So the calculation is a bit more complicated to account for all those changes. It's not a very simple task to do.